So thank you for the invite. I appreciate it. This is, I guess, well, anyway, I'm excited to be here virtually. So first of all, this talk is called Conformal Fundamental Forms. And based off of what I've seen, it might be a little bit more mathy than people may be familiar with, but that's okay. I'll try to provide all the background I can. So the majority of this talk is really based on work that I did with my advisor and a collaborator. This is on the archive at 2107.10381. Also, there's some upcoming work, both with the same collaborators that's also already gone out in the archive, as well as some work that I'm doing on my own that kind of continues this business. If I get there, I'll get there. If not, maybe not. So just some words of why I care about this. So generally, an understanding of the geometry of hypersurfaces, which is really what I'm talking about, is useful to better understanding boundary value partial differential equation problems. In particular, some of these partial differential equations are going to have conformal symmetries, and so studying hypersurfaces embedded in conformal manifolds is a useful thing to do. So I'm particularly interested in studying that geometry. So really, the picture that we're looking at is maybe you have some manifold, maybe it has some handles, you know, the typical picture. Call this manifold M gamma. And then we would have some hypersurface embedded in it. Maybe call it sigma. So I'm interested in the extrinsic curvature data or the extrinsic curvature information of how this sigma is embedded in the manifold M, in particular in the manifold M with conformal class of metrics. And I'll explain what these words mean if you're not familiar. Just to be clear, what I'm about to go over is really just a tiny little piece of a much larger program to understand the local and global properties of conformally embedded hypersurfaces. So this is obviously not the whole picture. And going further than that, all of my investigation is going to focus in this region here, the region local to the hypersurface. I'm not going to worry about any topological or global structure. So that's just a lot harder. So I'm just going to give you a quick brief outline of what the talk is going to look like. First, there's going to be some background information for those of you who are not as familiar with the differential geometry I'm going to be talking about. Then I'm going to give you the construction of these conformal fundamental forms after I tell you what they are. And then if I get there, which I'd love to, I'm going to give an application or two of why we might care about these things. So let's start with a background. So first, what we need to talk about is we need to talk about hypersurface embeddings. And it turns out perhaps the easiest way to describe hypersurface embeddings is with a defining function. So a defining function is the following. For sigma embedded in some manifold M, a defining function S for sigma. I'm going to use abbreviations. Stop me if there's any abbreviations that you think or that you don't know. A defining function S is a function that satisfies the following. Namely, for all P in M, so for any point in the manifold M, if S of P is equal to 0, that implies necessarily and sufficiently that P is in sigma. This just means that if you plug in a point P into the defining function S and you get 0, that point has to be on sigma and vice versa. It's just sigma is the, or S, sorry, S is the 0 locus of sigma. Also, one more condition is that the exterior derivative of S along the boundary sigma, or along the hypersurface sigma, that has to not be 0. And the reason why we want that second condition is just we would like to be able to use S, locally at least, as a coordinate that's transverse to sigma. So the picture, again, we have our surface, or our hypersurface sigma. Maybe this is where S equals 0, and then we'd like to be able to at least locally say maybe this is S equals 1, so that you can treat it as a coordinate that runs off of the hypersurface. Now, this is fine, and we could continue studying in this context, but I'm actually going to narrow our view a little bit to talk about something that's a little bit easier and perhaps more applicable to more physical systems. And that's the system when, or that's the supposition that the embedding is separating. Now, all that means is that we can erase the right half of this picture. It just means that sigma splits M in half. The reason we want this is because we want to be able to have, basically we want to be able to have a well-defined notion of into the bulk, meaning when you go off of sigma, that goes in a direction. This basically models the pictures that we see in ADS CFT, for example. So this is very, very basic Riemannian geometry, but I'm interested in studying conformal geometry, so we have to kind of do a little bit more work. We have to soup up this idea. So let's soup up the idea of a Riemannian manifold, and let's define a conformal manifold. So a conformal manifold, it's just like a Riemannian manifold, but it's conformal, perhaps no surprise. But what does that mean? It's a pair, a manifold with a conformal class of metrics gamma, which, well, a manifold's a manifold with a conformal class, CC, of metrics. And all a conformal class of metrics is it's just an equivalence class of metrics that are related in a particular way. So if you have two metrics, G and say G tilde, in your conformal class of metrics, all that means is that there exists some positive function, positive and smooth function, such that G tilde is omega squared G, meaning that there is some conformal rescaling of one of the metrics to get you to the other one. So if you had dx squared plus dy squared, a conformally related metric would be x squared dx squared plus x squared dy squared. Well, okay, that's not a good example because it's not strictly positive, but you guys get the picture. So this is what a conformal manifold is. So we're going to be studying objects that are a pair, M and gamma, where gamma is our conformal class. And then we just need one more thing to define our hypersurface. And in particular, we're going to use the same structure. We're going to talk about a defining function, but that's not quite all. And the reason why we don't just use a defining function again is that, in a sense, when we're doing general relativity or any geometric theory of physics, really our coordinates usually represent distances, just like how our metric represents distances squared. So if our metric represents distances squared, well, our coordinate should rescale in the same way as distances. In particular, we would like our defining function to rescale as well when we rescale the metric. So we need another notion of how functions, and in general, more general things like tensors and so on, will rescale when we choose a different representative of our conformal class. So I have to define another few terms, and then we're going to get straight into the meat of it. So I'm going to define what a density is. So a weight W density is an equivalence class let's call it tau. By the way, I'm going to be using Greek letters for the equivalence for the densities and for the conformal versions of the Riemannian things. I'm going to be using Latin letters for the representatives themselves. So tau might be an equivalence class, a weight W density. That looks something like this. It's a pair of a metric and a tensor T. And so in an equivalent equivalence class, another representative of the same equivalence class would be omega squared G paired with omega to the W T. So here we see that this thing T, whatever it is, maybe it's a tensor, maybe it's a scalar, rescales by omega to the W. That's what makes it a weight W density. Now, this thing lives in a particular space. It's a section of a particular bundle. In this case, it's just some arbitrary tensor bundle that lives on M. Oh, come on. That's supposed to be a T for tensor, not T for tangent. A tensor bundle that lives on M, and we say that it has weight W. So this is the notation that we use. By the way, this thing, it's just your standard tensor bundle on M producted with something that we call the density bundle, which is just a scalar valued bundle. It's an R plus, well, it's a ray subbundle really. But this is all just to say, this bundle represents the weight, how the thing rescales under rescalings of the metric, and this just represents the tensor structure. So that's what a density is. And then we just need to talk about what a defining density is so that we can actually complete our picture. So a defining density is exactly as it sounds. It's just like a defining function. Defining density, sigma, and this is just a scalar, but it's a weight 1 scalar. So it lives in this section space. This is a defining density for a hypersurface embedding in the conformal manifold, is a density with all of its representatives being defining functions. Which is just to say that if you pick a metric G, then its representative, then the representative S corresponding to that metric G of sigma is just some defining function. And there's a whole bunch of different defining functions, because you could multiply any defining function by, say, I don't know, 19, and that would be an equally good defining function. And indeed, multiplying by any positive function is also an equally good defining function. So we just lump them all into this thing called the defining density, and then it rescales in the way we would expect it to. It rescales like a length. So putting all of this together, we can represent a conformally embedded hypersurface as a triple, right? So the picture is we have our conformally embedded hypersurface, and this is not a picture, I'm sorry I said that. It's just an analogy. We can represent that surface by the triple M, its conformal class of metrics, gamma, and the defining density sigma. And that kind of really does contain all the information of the thing that we're trying to study. But there's a problem here. Namely, if I gave you this triple, oh, my pen stopped working. Oh, there we go. If I gave you this triple, and I gave you a similar triple, say M, gamma, and F sigma, where F is just some positive function, you wouldn't be able to tell apart the difference between the hypersurfaces that it's describing, right? Because if sigma is 0, then F sigma is 0, so long as F is a positive smooth function, of course. So the question is, how do we characterize a system represented by this triple if that system is not unique to begin with? Well, the answer is holography, because of course it is. In all of these things, all we do is holography. And what that means specifically is that we demand that, in this case, sigma, the defining density, satisfies a particular canonical partial differential equation in the bulk, in the larger conformal manifold. That means that we just like set some PDE, and then we say that sigma has to solve that PDE, and that PDE canonically determines exactly which F we want to choose. So the problem that we demand our sigma must satisfy is known as the singular Yamabe problem. Now, there's a lot of discussion on this in the literature. I'm not going to give you all the references, in part because the literature is 3 times as old as I am, and it's hard to keep track of all of it, but I could find the references if anybody's interested. The problem is stated as follows. Given some triple that represents our conformally embedded hypersurface, we want to find a positive function f such that the singular metric, I have to tell you what the singular metric is. The singular metric is defined as G naught. It's gamma over F sigma squared. So gamma meaning you take a representative of your metric G, and then you divide it by F times the equivalent representative of your defining density sigma. And that'll just be some well-defined and unique metric. We want that this metric satisfies the following criteria. And this is what makes it a PDE. Its scalar curvature should be equal to minus d times d minus 1 away from the hypersurface. It's clearly the singular metric is not defined along the hypersurface. It blows up, it goes to infinity. So we just want that the scalar curvature is constant, very, very close and nearly up to the boundary, but not quite there. And so it turns out that solving this problem, finding this f, uniquely determines your sigma. So in particular, you would find the f, multiply your original sigma by that f, and that's your new sigma. And that it's unique, at least it's mostly unique, up to a certain order, and I'll talk about that later if I get to it. And so this is our canonical sigma. So going forward in what follows, we're going to assume that this triple that we're talking about is the one that solves this problem, because you can always do this. You can always solve this problem, and it uniquely picks out your sigma.
What is D?
Sorry?
What is D?
Oh, sorry. Yeah. D is the dimension of our manifold, of the manifold M.
And so scalar curvature should be negative.
Yeah, it is.
It is, okay.
Yeah. The scalar curvature is negative here. Right, so that's probably enough background, at least I hope. And so we're gonna just jump right into the construction of these fundamental forms. But we're actually not going to do that. I lied, because maybe not everybody knows what.
Before you go,
sure.
What's the dimension of sigma?
D-1. It's a hypersurface, so it's going to be codimension 1.
Okay. Yeah.
Yeah. I'll put a little D-1 here. Sorry about that. Right. So maybe not everybody knows what a fundamental form is. This is not a term I invented. It's a commonly well-known term in Riemannian geometry, but maybe not everybody has taken that class or thought about it in a dozen years. So I'm just going to give a quick, really light overview of how of why we might care about these things in Riemannian geometry. So just like we did above, where we started with the defining function and then we souped it up to talk about conformal defining densities, we're kind of going to do the same thing with these fundamental forms. So the question is, how do you study hypersurfaces, embedded hypersurfaces, in a standard Riemannian setting, the Riemannian manifold and all of that business? And again, the reason why I introduced this to begin with is an easy way to do it is with the defining functions. So I'll write a little note up here for myself to remember what I'm doing. So let's just look at a very, very simple example. So let's say we have a hypersurface sigma embedded in a flat RD, right? And we're going to have that S, the defining function for sigma, is unit defining. All that means is that it has length of 1. Now this can always be done. You can always solve this problem to arbitrarily high order if you want. So we're just going to assume that this is what's done, just like how we can assume that you can always solve the singularity-Mabi problem. Right, and so the way that we're going to study this particular embedding is by studying the jet coefficients of S. Now, very roughly speaking, a jet coefficient is basically like a local Taylor series expansion of S. So you would look at the derivatives in all of the different directions restricted to the boundary. So in particular, we can just start taking derivatives of S and see what it looks like, see what those tensors end up looking like. In particular, our first jet coefficient, something that everybody's probably familiar with, it's just going to be our our derivative on S. It's just the conormal. In this case, the conormal has a unit length, so you might call it a unit conormal. This is going to be our first jet coefficient. It's just one derivative. And really, this particular object is nice and it's useful for studying the hypersurface because it tells you how to project between the bulk space between in this case RD, and sigma. It tells you how you can take a tensor on R and project it to a tensor on sigma. Another useful tensor that shows up in this setting is something called the second fundamental form. Now, sometimes you'll see it written as an S with a shape operator with an index up and an index down. I'm going to be representing tensors with this abstract index notation, and I'm going to be using the metric to raise and lower indices as one normally would. So try not to think too hard about what's going on here. Everything's relatively straightforward with regards to indices. But this second fundamental form, I write a Roman numeral 2, and it's defined, at least in this simple setting, as just a Hessian of S. And then you can restrict it to the boundary. This thing, like I said, it's called the second fundamental form. It's going to play a big role in what's to come. It's our prototypical example of a fundamental form. And the reason we care about this is it shows how the projection map changes as you move along the hypersurface sigma. Also, this particular object shows up really frequently in all of these classical differential geometry equations, things like the Gauss equation, where and the Gauss formula, like in relating the Riemann curvature tensor in the bulk to the Riemann curvature tensor on sigma. This guy shows up frequently. Now, this is usually about where it stops in a differential geometry class, but I'm a physicist by training, so I'm just going to keep going and see what happens. So the next thing that we could reasonably ask is we could do 3 derivatives, right? But that's where things start to get a little hairy. In the case of the second fundamental form, we didn't have to distinguish between a transverse, i.e. normal derivatives, and tangential or hypersurface derivatives because we assumed that n was already unit length. So if you took a transverse derivative of n, you'd get 0. However, this second fundamental form doesn't have any transverse invariant properties. So you could, in principle, ask if you have a foliation of given by S equals a constant, you could ask how these second fundamental forms change as you move to different foliations. Similarly, you could ask how the second fundamental form changes as you move along the foliation. This would be the picture where you have your foliations like this, you could ask how the second fundamental form changes as you move up and down, or you could ask how it moves off. And so it turns out, for technical reasons, studying how the second fundamental form moves along the hypersurface, less interesting to me than transverse to the hypersurface. So we're going to dig into those transverse bits. So we're going to ask how the second fundamental form changes as you move off of sigma. So to do that, we have to take normal derivatives of the second fundamental form. In particular, our first example would be the negative of our normal derivative. This nabla n, this just means you take the normal, or you take the covariant derivative in the normal or in the n direction. And we're just going to act with that on the Hessian of S. It's a totally reasonable thing to do. Turns out, it's an easy calculation, this is equal to the second fundamental form squared, just via matrix multiplication, right? Now, this isn't often done, but there is some evidence for calling it this. Sometimes this thing is called the third fundamental form, Roman numeral 3. And really, this is the third transverse jet coefficient. You could have taken a derivative along sigma. I chose to take a derivative perpendicular to sigma. Fine. And so you could keep going, because why not, right? We can play this game. In fact, if you have -1 to the k over k factorial, and then you have k normal derivatives on the Hessian of S. Oh, I'm missing an S. Well, turns out that that's the second fundamental form to the k plus 1, as matrix multiplication goes. And I'm just going to give this a name. I'm going to call it the k plus 2 fundamental form. I don't know how to write in Roman numerals what k plus 2 is, so I'm just going to write k plus 2. And this is just another a higher transverse jet. The thing is this isn't particularly interesting. Like all of this business that I've done so far isn't interesting because it's just the second fundamental form to various powers. So it doesn't give us.
Can I ask questions as you go along? I mean,
sure.
Do you mind?
By all means.
How do you take the square of pi AB?
Oh, so it's just all I mean is matrix multiplication. So this would be pi AC,
so you
pi
don't
CB.
have a 4-index object.
No. So yeah. So what I mean is we're doing matrix multiplication. So you do your standard row column multiplication business. And so then the cube you would stack up 3 of these, BD, and then to the 4th power would be 4 of these, and so on. So it's always 2 indices. We're just squaring over the intermediate indices. That's all. Does that help?
Thank you.
Oh, okay. Right. So this isn't interesting. Like I said, like these are just higher and higher powers of the fundamental form. It's just a not interesting thing. It doesn't contain any extra information. But that's until you realize that we were working in a flat background. So instead, if we replace our flat background with something more interesting, say just some arbitrary manifold with some arbitrary metric, well, now things get a little bit more interesting. In particular, this third fundamental form, this is, well, it still has the same leading term. It's still the square of the second fundamental form. But now it has a term that involves the Riemann curvature tensor. So here, this notation means I'm contracting an n into the 1st and 4th indices of our Riemann curvature tensor that you would typically see in a general relativity class. Then you have the 2 middle indices are free or floating. And you could keep going. And this would imply that the higher fundamental forms, these are going to probe not just what's going on at the boundary, but it's also going to include data about what's going on near the boundary. It's going to tell us what the curvature is like near that hypersurface. So why does this have anything to do with conformal geometry? Well, the thing is this discussion I just gave, this is like done. This is a thing that's been well known for a good long time. It's more or less solved. If you want to construct all of the hypersurface diffeomorphism invariants, which is something I'd like to do for the conformal case, you just stack on a whole bunch of derivatives and call it a day, because those things are by construction diffeomorphism invariant. The trouble is conformal geometry isn't that easy. For example, a covariant derivative in general is not conformally invariant. It doesn't take something that is a density and maps it to something else that is a density. It just doesn't work. It's a lot harder. So the question is, how do we study these same sorts of objects if we want to characterize things like the relationship between the bulk conformal curvature with the hypersurface conformal curvature, all of those things? If we want to make those sorts of relationships, and if we want to study these invariant quantities, we have to do a little bit more. So I am going to use this method of finding these fundamental forms in the conformal case, but it's messy. So In order to do this, first we need a notion of a connection on a density. And it turns out that it's like, I'm sweeping a lot under the rug here, but it's really not that bad. Like, we would just write, if we have some density tau, nabla on tau, you could just think of that as G, the equivalence class of G with nabla on T. It's not quite a density, but because we're only going to be dealing with conformally invariant things anyway, like this is just a totally fine thing to do. And there is a rigorous definition of all of this, but I'm gonna shove that under the rug because I'm already running out of time anyway. So with that said, we can just start hitting the defining density with derivatives. So let's start and see what happens. We're going to define NA now. This is going to be our first jet coefficient. This is just nabla A on sigma along the boundary. Okay, turns out, and you can check this for yourself, if you rescale S by omega, how does N rescale? Does it scale as a density? The answer is yes, it does, as long as you restrict it to the boundary. So it is just in the conormal bundle of sigma along the conormal bundle of sigma with weight 1. It's great. Like, we're off to a great start. The next question is, what can we do next? Well, maybe we try to write down that the second fundamental form. Is this just the Hessian of sigma? Well, we have to be a little bit more careful if we want this to match the standard definition, because we don't necessarily have the n squared equals 1 condition anymore. We have to be a little bit more careful. In this case, we're going to restrict it to the tangent bundle of sigma, sorry, the cotangent bundle. But even if you do that, you're still stuck, because this is not density valued. The space that it would live in would be the symmetric rank 2 cotangent bundle log sigma, weight 1, but it's just not in that space. It doesn't rescale like a density would. By the way, I'm going to call this bundle, I'm going to call it f of sigma with a 1 there. I'm going to be using this bundle over and over again. It'll show up frequently, so I'm just saving for shorthand purposes. So replace the 1 with whatever weight you want, replace the sigma with whatever manifold you want. The thing is though, this is actually a pretty easy problem to fix. The second fundamental form is not density valued, but it turns out its trace-free part is density valued, and hence it is conformally invariant. So all I'm going to do is I'm going to define the trace-free second fundamental form. That's what that little circle means. I'm going to define this as the trace-free part of the Hessian of sigma, restrict it to the cotangent bundle of sigma, and then miraculously, this is an f sigma of 1. And again, this is something that you could probably explicitly check. It's not that bad to check. If you rescale sigma by omega, 2 naught also rescales by omega. Great. So the question is, can we keep going like we did before? And unfortunately, the answer is no. So this is about as easy as it gets up to here. The trouble is that like you could just try to take a normal derivative of this thing and then see what terms you have to add. But as you add more and more normal derivatives, in order to maintain conformal invariance, you have to just keep on adding more and more terms, and you have to basically guess and check what the coefficients are to get it to be conformally invariant. And that's not easy. Like it's not even tractable to do because the number of terms explodes combinatorially. So alternatively, what we could do is we could define some sort of canonical extension of this thing. Oh, come on, my pen stopped working. There we go. We can define a canonical extension of the second fundamental form, because as is right now, we can't take normal derivatives of this. It only lives along the boundary, so you can't take normal derivatives of it. But if we define a canonical extension of it, then we can perhaps take some sort of conformally invariant normal derivative. Like I said, derivatives are not conformally invariant on their own, so we would need to come up with an operator that does that for us, that is conformally invariant, that maps densities to densities. Fortunately, that's what I did. So we know how to do it now. So just as a quick note, there's good reason to understand why this thing is not going to be conformally invariant in the bulk. Like you can't just take the trace-free Hessian of sigma and expect that to be conformally invariant. And the reason for that is that the conormal is not being restricted to the boundary, not being restricted to sigma. That's not a density. Only when you restrict it to the hypersurface does it become density valued. Because otherwise you would get some term that looks like d omega when you rescale the metric. It just doesn't work out. And so taking a normal derivative of that, there's no a gradient of that, there's no reason to think that it would produce something that is conformally invariant. So instead, we just have to figure out what we can add to this thing, to this quantity here. What can we add to that to fix the conformal invariance away from the boundary, but maintains conformal invariance on the boundary, so that the whole thing would be conformally invariant in the bulk in M. And it turns out there's actually a pretty easy fix. You just have to add one term. So what we're going to do is we're going to define our canonical extension of the second fundamental form as it's a density valued thing, and it is the trace-free Hessian of S. That's the thing that we wanted it to be, plus something proportional to S, which won't interfere when we go along the boundary, plus S times this thing called P, known as the Schouten tensor, the trace-free part of that as well. This Schouten tensor, by the way, and I'll define it in a minute. This Schouten tensor, it's just a trace correction of the Ricci tensor. So it's 1 over d minus 2 times the Ricci tensor minus the scalar curvature times g over 2 times d minus 1. It's just a particular combination. It shows up really frequently in conformal geometry, so that's why like this particular combination shows up here. There's nothing super special about it. Right, so now we have an extension of this second fundamental form, so we can take normal derivatives. The question is how, and the answer is lots of work. So we're really, so the next step is to answer the question, does there exist an operator? Call it delta k. And that operator has to map fm1, because that's where the second fundamental form lives, to f sigma 1 minus k. This would just be the natural weight of the normal of k normal derivatives on our second fundamental form. With leading derivative, or with leading term rather, we want it to look like k normal derivatives on our second fundamental form, or extension thereof. So we want to know if such operators exist. And you might naively say, well, of course they do, but you'd be wrong. In fact, a result from Peterson and Gover in 2018 showed the same sort of thing for operators on scalars, which is dramatically more simple, but they did lay out the foundations for my work. The answer is not always. There is not always such an operator. In fact, I've explicitly characterized when such operators exist. So for all dimensions d, that's not how you spell all. For all dimensions d, there always exists operators delta k for any k between 0 and d minus 1 over 2. So you can go about halfway up the dimension before you run into trouble. It's just the fact, it just happens to be that way. It turns out that there's a relatively famous first example. This is something known as the Raban operator, which mixes Dirichlet and Neumann operators. So there is interest in what these operators are just in general. I'm not going to talk about it though, because I'm running out of time. However, things get messy when you get to higher values of k, when you want to take more and more normal derivatives. You can't keep going forever. Computing these things get messy, but there is some explicit iterative formula that I've written down. It's not that great, but it is what it is. You can do this in general up to this value of k. However, for all, so with this operator, we can actually define the conformal fundamental forms, the subject of this talk. So that is, for all 0 less than or equal to k less than d minus 1, we define the conformal fundamental forms. I'm going to call them CFFs, because I don't want to write out all the words. So we will call the k plus tooth fundamental form. It has to be trace-free. This is the roughly k normal derivatives on this extension of the trace-free second fundamental form. And this indeed does live in f sigma of weight 1 minus k. And then you can ask, well, what about the higher ones? What about if you want to go higher than just d minus 1 over 2 normal derivatives? Well, turns out there's some trouble here, right? So for an even dimensional bulk manifold, we can actually always construct delta k for 0 less than or equal to k less than or equal to d minus 3. We can go further, basically, for even dimensional bulk manifolds. But for odd dimensional bulk manifolds, we run into trouble again. In fact, those operators just fail to have the correct number of normal derivatives, except in very specific cases. In particular, if the lower half of these fundamental forms, so these ones are the ones I'm referring to as the lower half, because you can go all the way up to d fundamental forms. If the lower half of the fundamental forms vanish, if they're all identically 0, well then these higher fundamental forms in the odd dimensional case, they do happen to exist. We get things that are called conditional conformal fundamental forms. And there's an interesting story there. Like it's bizarre how you get this parity phenomenon happening, but this is well documented in this sort of thing, especially when dealing with conformal geometry. And in fact, I even have a formula for the first four examples of these fundamental forms. I'm not going to tell you what they are because again, I'm running out of time, but I'll tell you what the third fundamental form is, and maybe it'll look familiar. So the third fundamental form is minus the trace-free square of the second fundamental form plus the Weyl curvature tensor with two n's hooked in. This would live in f sigma of 0. This one always exists regardless of dimension, by the way, assuming you're in dimension d greater than 3. And that's where we usually work anyway. So this should look familiar because this is basically just a correction to the third fundamental form we saw in the Riemannian case, which is awfully nice. Here we have the Riemann curvature instead of the Weyl curvature, and we didn't have the trace-free square of the trace-free second fundamental form, but the structure is the same. And you can just keep taking normal derivatives, and I've done that, and we can study those objects and what they do. So, but this is what those fundamental forms are. Now, I promised that I would have some applications for you. So let me tell you one in the next like 3 minutes that I have. I think I have 3 or 4 minutes left. So let me give you one application. This is the one that was discussed in the paper at the very beginning. I won't get to the end or to the last application.
I can borrow some time from Q&A session, by the way, if you want.
Sorry, one more time?
If you want, you can borrow some time from Q&A session.
Oh, okay. If I need it. There's not much to say about the second application anyway, because it's still a work in progress. So I don't want to give away too many details. So let's talk about the first application, and perhaps it's a really nifty one. So we're going to assume that you're given a triple, and we're going to assume that that triple solves the singular Yamabe problem as we usually do. Then from the singular Yamabe problem, this gives us a canonical singular metric. This is the gamma over sigma squared metric. It's just our standard metric. And so you can ask the question, when is G0, this metric, Poincaré-Einstein? Now, I don't know how much you guys have read of Pfefferman and Graham, but this is the thing that they invented. And so if you're not familiar with what a Poincaré-Einstein metric is, let me tell you, it's a really nice metric. It's a metric that is roughly hyperbolic, but also it solves the Einstein equations. So Poincaré-Einstein metric in this case just means that it's a metric G0 that satisfies the following differential equation. The Ricci curvature of G0 should be equal to minus d minus 1 times the metric itself. Basically, the Ricci curvature is pure trace. And of course, this is only on m minus sigma. So you could reasonably try to answer this question, but it turns out, like a lot of these things, answering this question explicitly requires global data, meaning that you have to know something about what's going on deep in the bulk, what the topology is and things like that. And I don't like answering that stuff, at least not yet. So I'm gonna try my best to answer a question that only requires local data. So we can ask the question, when can you get asymptotically close to solving this problem? And the answer is actually relatively straightforward. So if we instead ask for asymptotic Poincaré-Einstein, APE, i.e. we want that the Ricci curvature is minus d minus 1 times G0 plus order, say, sigma to the d minus 3, then this answering when such a metric is asymptotically Poincaré-Einstein in this sense, this can be answered purely by local data. And in fact, there's some previous results known about this question. Work by LeBrun in 82, by Rod Gover in 08, by Chap, Gover, and Hammerl in 14. There's a whole bunch of work on this. It turns out that we knew some conditions we knew some implications of when this is true. It turns out that if G0 is APE, if it is an asymptotically Poincaré-Einstein metric, then that means that the second fundamental form and the third fundamental form both have to vanish identically. They didn't know that this thing 3-0 was called 3-0 at the time. They called it the Fialkov tensor, but this is a thing that was known. It turns out, and this is the new result from our paper that we put out a few months ago, the new result is the following. And I mean, this is really a theorem, and it has a bit of work to prove, but it can be succinctly summarized that G0 is APE if and only if the second fundamental form all the way up to the D-1th fundamental form vanishes identically. And so what this really does is it tells us that the fundamental forms they characterize the failure of a metric to be Poincaré-Einstein, or at least asymptotically Poincaré-Einstein in a local sense. So it's not only do these fundamental forms just kind of show up as natural curvature invariants or extrinsic curvature invariants, they actually characterize the manifold itself and what type of manifold it is. And people care about these Poincaré-Einstein metrics. Like there's been a whole bunch of study into them, especially because these are the things that show up pretty frequently in the ADS-CFT correspondence. I have one more application, but it requires a bit of setup. So I think I'm going to end it there, and I'm going to thank you for your time. And I guess I'll open it up to questions, I suppose.